Recording in progress.
Okay, so we've got lecture today. We've got a break tomorrow. We've got lecture in person on Friday, and that's our last in-person meeting. We have a test on Monday. I looked at so there's those things on the horizon. I have not downloaded and uploaded yesterday's lecture. I will do that just a little bit after class. So I'll link that. Next item is, it looks like, I would say 75% of the class took their first quiz, and around, a little bit more than that took their second quiz. You have until 2 p.m. today to complete that second quiz. In the event that you missed one, I always drop at least one. I mean, typically if I have if I give, 8 quizzes, I'm gonna drop one. So then you can kind of extrapolate that out and say if he gives, 16, and gonna drop 2 or 3. And keep in mind that the quizzes are really kind of the mechanism for homework and to review the material every day. What we're going to be talking about today is we will kind of transition to talk about basically how things form. We'll talk about the periodic table and how compounds form with one another. What types of compounds and kind of scientific laws are there about different compounds? So I want to make sure that I'm sharing the right thing as opposed to, good, I am. So scientific laws to get things kicked off. We have this right here. So if we look on the left-hand side, we've got a piece of glass where this is known as an Erlenmeyer flask. How it's kind of got a wide bottom and then it curves up and then has a narrow opening at the top. And then on the right-hand side, the other piece of glassware that we have containing the kind of darkened solution, that's a graduated cylinder. Graduated cylinders vary quite a bit. They can be 10 milliliters, they can be 100 milliliters, they can be 1 liter, 5 liters. I'm sure that there are larger ones than that, but the pretty standard lab fare is about 50 to 100 milliliters. This one right here looks like it's 5, 10, 15, 20. It's a 25 milliliter graduated cylinder, which actually is shown right there, 25 milliliters. So we've got our clear solution in our Erlenmeyer flask, our darkened solution in our graduated cylinder, and the total mass, everything that's on top of this digital balance, is approximately 173.64 grams. Now, just to review a little bit from yesterday, could we translate or convert that number to scientific notation? Yes or no? Yeah, we could. And what we want to do is we want to take our decimal place from between the 3 and the 6 and move it to the left 2 positions, because for scientific notation, we have 1 numeral, decimal, and then everything that follows. So we have 1.7364 times 10 to the, would it be a negative or a positive? Would be a positive, because our whole number, our complete number is 173.64. If we kept the units, if we said 1.7364 grams, we would want to say 1.7364 times 10 to the positive 2 grams, because we didn't change the unit. Now, we've got 173.64 grams. Then what we'll do is we'll transfer the contents of the graduated cylinder to the Erlenmeyer flask. And oh, look, the solution, when combined when the solutions are combined, they're darker than the solution in the graduated cylinder. That's the intent, what we're supposed to see. Can everyone see it's a little bit darker? So this is a reaction that's taking place. What's the mass? It's the same. So essentially what that's trying to convey is that when you add these 2 components to one another, the mass doesn't go up, the mass doesn't go down. The 2 contents were simply combined into one container, and we didn't lose anything in the process. Now that relates to the law of conservation of mass. Here is another display of that. And the overall kind of theme or phrasing or explanation for the law of conservation of mass is matter is neither created nor destroyed during a chemical change. Okay, that last word there, change, that's a pretty important one because there can be a reaction where you add two components together and you see the mass go down. Oh, that's kind of funky. That's entirely possible to happen because if a gas, let's say that we added these two reactants to one another and a gas was produced, and that gas leaves that container, and maybe a lot of it's produced. Does a gas have a mass? It does. Just like, think about it as you get a propane tank. When you pick that propane tank up from HEB, and then later when you return it to HEB, it's a whole lot lighter after you used all of the propane gas in there. Does that make sense? So in the event that you have a reaction where a gas is produced and is released from our reaction, that's possible. Your mass will go down. But if nothing like that happens, then, well, the mass and the contents are the exact same. Does everyone follow that? So here what we have is a reaction of 100 grams of mercuric oxide. Now, if we react 100 grams of that, we will get 92.61 grams of mercury. So mercuric oxide is a compound that's made up of oxygen and mercury. Mercury is one element of the periodic table. That's Hg. Number 80. And this one is always kind of tricky because I go over here and then, so I'm sorry, play along over there. Okay. So Hg is what mercury is on the periodic table. So we've got a compound that's made up of mercury and oxygen. And if you were to put this under or put this over a open flame with a Bunsen burner, well, what's going to happen is that mercury and that oxygen are basically going to separate. That oxygen is going to be released as O2. And with the right piece of instrumentation, you can capture that gas. So from that 100 grams of mercuric oxide, you get 92.61 grams of mercury and 7.39 grams of oxygen. So my question for y'all is, did we lose anything when we burned? Did we lose any mass when we burned 100 grams of mercuric oxide? Nope. Our mass was conserved, 92.61 and 7.39 grams. So the total mass was conserved between these two things. Now, in the event that we scaled our experiment up, and we, rather than doing 100 grams of mercuric oxide, we use 200 grams of mercuric oxide. Do you think that the mass of mercury that is produced is going to increase? We're starting with more of our starting material. What about the mass of oxygen? Yeah, our starting amount doubled, so each of these two output components is going to double. So we're going to end up with approximately 185.2 grams and 14.8 grams of oxygen. Now that heat exposure, well, this is where people might have a misconception or might get mixed up. If you have 100 grams of mercuric oxide and you put it over a heat or put it over an open flame, burn off that oxygen, you're going to be left with mercury. If you don't have any way of capturing that oxygen, you might say, oh my gosh, I destroyed matter. Did you actually? Did you? Did you? You know it. You just didn't have the means of capturing it. So, we're good with that? Awesome. Yeah, we'll skip that. Now, laws of chemical combination. The law, so that's our first law, the law of conservation of mass. So your input mass and your output mass, that's going to be equal. So if you put 100 grams in, you're going to get 100 grams out. that 100 grams might be organized in different things, but it's going to be released. Now, the law of conservation of, or so the laws of chemical combination, we've got conservation of mass, where here we have 3 different reactants kind of reorganize themselves to make 2 different products. The total number of orange balls is 4 as a reactant, and then this arrow indicates that a reaction is taking place. At our product side, we still have 4 orange balls, 2 gray ones, 2 gray ones. So we've conserved the total mass that was input and what was ultimately output. We also have the law of definite proportions and multiple proportions. These laws, in effect, have to do with ratios. They have to do with ratios of how different elements combine with one another. For example, when I was in 5th grade, my brother told me, hey, do you want to bleach your hair? And I thought to myself, yeah. In retrospect, my hair was very blonde then. I probably didn't really need to, but he was like, it's cool. And I was like, you're older than me, so you're an authority on coolness. How do I do this? He said, you get hydrogen peroxide and you just pour it in your hair. And I was like, okay. Hydrogen peroxide is a compound with a formula that is H2O2. So that's 2 oxygen atoms and 2 hydrogen atoms that come together to make hydrogen peroxide. Now, does that formula look similar to anything that you've ever heard of or seen before? Water, H2O. So these 2 compounds, H2O2 and H2O, are dramatically different from one another. Has anyone ever poured like hydrogen peroxide onto like an open wound or something like that? Kind of fizzes up. And the intent is that it's killing any sort of bacteria in there, or oxidizing stuff in there. Has anyone ever poured water over an open wound and noticed that same sort of bubbling? No, because water doesn't do that. It doesn't have the same effect. So hydrogen peroxide and water are fundamentally different from one another. They're both made up of hydrogen and oxygen, but the ratios of hydrogens and oxygens to one another are different, and they give these 2 different compounds fundamentally different reactivities. So when it comes to definite proportions, that is basically looking at water is always going to be 2 hydrogens and 1 oxygen. Whether you have, 1 single molecule of H2O or 10 liters of H2O or 10 liters of water, it's nothing but a bunch of H2Os in there. So that's your defined proportions. Water is always H2O. Multiple proportions is really kind of reflecting on, well, you can reassemble and rearrange different atoms with one another to make different compounds. H2O is an oxygen and hydrogen containing compound. H2O2, hydrogen peroxide, is also an oxygen and hydrogen containing compound. They are different from one. So definite proportions has to do with this specific compound has this specific ratio of atoms to one another. Multiple proportions are, there are a number of different compounds that are made up of oxygens and hydrogens, and they have different ratios to one another. Does that make sense? Okay. So the composition of water always yields 88.8% oxygen and 11.2% hydrogen by mass. So those are a percentage, that's effectively a ratio. This illustrates the law of conservation of mass, definite proportions, or multiple proportions. Now, if you think that it is A, the law of conservation of mass, put your right hand up. If you think that it's C, the law of multiple proportions, put your left hand up. If you think that it's B, the law of definite proportions, ride the roller coaster of excitement by putting both hands up. So on 3, after I read the question, 88.8% oxygen, 11.2% hydrogen, that's the composition of water. 3, 2, 1. Woo! So this is saying that water is always going to have that specific ratio. It's going to be 88% by mass oxygen and 11.2% by mass hydrogen. That's why this is, whenever I see definite, I always think of definition. Like this is defining what water is. Does that make sense? Okay. Now this is kind of projecting outward because we haven't really talked about masses of oxygen or hydrogen or anything like that yet. But we will, but this is just giving kind of a definition, a mass definition or percent mass definition of what water is. Does everyone follow that? Great. Now, here, there are 3 different oxides of iron. For a fixed mass of iron, the masses of oxygen in 3 different oxides give the ratio 6, 8, 9. This illustrates A, the conservation of mass, B, the law of definite proportions, or C, the law of multiple proportions. Now, before we answer that, let's jump back a tad. Definite proportions are this specific compound has this exact ratio. Multiple proportions. This specific compound has this ratio. This other similar compound has this ratio. Another one has this specific ratio. Does everyone follow those? And I just had an idea. Let's see if I can do this. Okay. Has anyone ever seen one of those cars? I think they're called slingshots. They have 3 wheels. Is that a car? It's not a philosophical question. Yeah, we're gonna go with it's a car. A slingshot, by definition, we'll go with has 3 wheels. A truck, by definition, we'll go with a dually truck just to make it interesting. A dually truck, by definition, has 6 wheels. They are both cars in the general sense, but you have definitions for each one of them. Does everyone follow me there? They both fall into the category of vehicles and drivable vehicles, but they are different from one another. They're made up of the same parts, but they are different. Does everyone follow me there? Okay. So now, you have a definition of what a slingshot is, you have a definition of what a truck is, but you're building them from the same parts. Here what we have, 3 different oxides of iron. So, actually, before we proceed, let's go ahead and answer it. Right hand for A, law of conservation of mass. Left hand for B, definite proportions, or ride the roller coaster of C if you think that it's multiple proportions. 3, 2, 1. Aha. Everyone voted for C. Just got to let you know, the time's going to come whenever I prompt you with, oh, ride the roller coaster, and everyone's going to be like, well, that's what it is, and you're going to be wrong. But for this is it. So this is saying, and I suggest that when you read questions, you kind of take this information and say that's intentional. There are 3 different oxides of iron. From there, that stem of the question, unless it talks about some sort of reaction, I'm going to dismiss law of conservation of mass, because the law of conservation of mass is related to here's a reaction and here are the products. The total mass of your reactants and your products are equal to one another. Definite proportions. Well, only if this question went on to say one of those oxides is this percentage and this percentage. Would I then say, okay, well, that's got to be what it is? Instead, this question goes on to say for a fixed mass of iron. So what that means is we have a certain amount of iron, and then the masses of oxygen in these three oxides give a ratio of 6, 8, 9. So if you wanted to try to determine what this is almost from like a molecular level, you could say that we're putting together a compound. And that compound is, there's one iron. And then there's oxygen in all of them. And those oxygens are 6, 8, and 9. So we have multiple proportions. We have iron paired up with 6 oxygens, iron paired up with 8 oxygens, iron paired up with 9 oxygens. The amount of iron was fixed. That did not change. The amount of oxygen gave us these different ratios. This ratio of 6, 8, and 9. Does everyone follow that? So that's where this question went. So C is our correct answer. Now, all of these theories all of these were put together with John Dalton's atomic theory, which the great thing about any sort of scientific theory is, and this is something that I think we struggle with as scientists, because we're like, oh, well, that's the rule. No, that's the theory. That theory is going to ever be evolving. If you find something that's contradicting that theory, you have to make sure that what you did was sound. Everything about the technical aspects of your experiment were true. For instance, if I was like, oh, well, that water bottle fell in this amount of time. Oh my gosh, gravity's not real because it took longer for this water bottle to go from here to here. And I'd be like, well, no, actually, the problem was that I threw the water bottle up in the air, and that's why it took longer. So I haven't really debunked gravity yet. But scientific theories are ever evolving. So Dalton's atomic theory basically reflected on and gave rise to those different scientific laws. Those scientific laws have been refined since, I think, John Dalton was alive in the mid 1800s. So it's always good whenever someone, refines an idea from like the 1800s, because it probably needs to be. Okay, so these laws, though, this, from what we've looked at so far, if you understand these 3 theories, conservation of mass, or these laws of definite proportion and multiple proportion, if you understand those, you're going to be in good shape. I always kind of think about examples that take me out of looking at something on a molecular level. Like for conservation of mass, I think about, okay, well, if I'm going to make cookies, here are all the ingredients that I'm going to use. If I weigh those cookies out, weigh all the ingredients of those cookies out, then my total mass is going to be X. Split it up into 18 different cookies. Okay, those 18 cookies were made up of all these components. The mass of those 18 cookies, chances are, is going to be very, very close to my starting mass. Is there a chance that it won't be? Yeah. And here's my folksy, silly joke. Because I've got kids and they like eating cookie dough, and I do too. See, that's silly. People like that. In addition to that, you use some water when you put the cookies in the oven, some of that water is going to evaporate. So your mass is going to go down. So anything that you can do, any examples that you can come up with that go outside of this scientific or of this chemical realm, I think is going to be beneficial. All right. Is everyone good with those laws? Fantastic. Just a second. The periodic table. Here it is. As you can see, the version of the periodic table that we have in here is actually lacking a little bit. what it's lacking is 4 elements. Those 4 elements there on the periodic table are real. They have been ptable.com. They have been added since these were printed. The ones that are missing are neohonium, number 13, moscovium, number 115, tennessine, and oganesson. Does anyone want to guess where tennessine was discovered? You're right, Tennessee. It was researchers at Vanderbilt University. These last elements down here, basically from like 109 to 118, those are elements that they're, you know, if you go out to like Enchanted Rock and you're digging around, you're not going to stumble upon some Tennessee. And not because you're in Texas, not in Tennessee, but instead because these are like stable for a very short amount of time. And I'm not talking like an hour or a day, I'm talking like to use some of our terminology from yesterday, like nanoseconds or femtoseconds. So it's it can form an atom, but it's only under very extreme conditions for one millionth of a second. But it counts. It counts. It counts. So ptable.com, I think it's a really great resource to visit for the periodic table because of the fact that when you go on any of the elements, you go there and the Wikipedia entry pops up, and that's chock full of information. Now, back to the periodic table. Okay, so which image represents an element? We look at A, we've got a pink ball and 2 gray ones. Typically, whenever we're looking at something that has a ratio of 1 to 2, it's either going to be water, H2O, or carbon dioxide, CO2. And so those carbon and oxygen, hydrogen and oxygen, those individually are elements, but they make up a compound in model A. B, 2 green balls. Well, that's an interesting proposition because it's something made up of 2 things, but those 2 things are identical. And then let's go down to option C. Well, here we've got a mixture of green and I guess that's a white, and then an individual grays floating around. Well, which one of these is your best option for an element? I think that there are some folks who are going to look at C and they're going to say, well, I'm picking C because of these gray balls there. Those individual ones, that's an element. And I'm answering this and ignoring the other thing, because I think that it's a trick question, and you, Dr. Gray, are out to get me. You just want to crush my dreams. Why? Put that at bay. I don't want to crush anyone's dreams. Your logic there is not flawed, but you got to take into consideration everything that's there. There's 2 different things in that box labeled C. So you want to say, oh, well, it's that individual gray ball. Yes, if this box was filled with nothing but that one, you'd be dead on. That'd be a great answer. But that's incorrect because of that other one. A, we kind of dismiss that as well, because that was 2 different elements that would make up a compound. So then by process of elimination, we're left with B. B has 2 green balls making up one entity, one thing. That's our correct answer there. You might look at that and say, oh, well, that's a molecule. That's a compound. Not wrong. But those 2 things come together to make one complete element. There's a couple of different compounds like that. There's, on the periodic table, there are a number of things. They're known as diatomic gases or diatomics. When I was in high school, my teacher had on her wall an mnemonic for your diatomic elements. And it was a picture of a person with a mustache. It was a drawing of a mustache. And this was a character. And this character's name was H. Braun Cliff. So H. Broncliffe, these are all of the different elements on the periodic table that are diatomic elements. Hydrogen, bromine, Br, oxygen, O, nitrogen, N, chlorine, Cl, iodine, I, F, fluorine. Those are all elements that when they exist in the atmosphere, they are going to exist not as an individual iodine, but instead as I2. Cl, chlorine gas, for instance, is Cl2. Bromine is bromine gas, Br2. Fluorine, F2, oxygen, oxygen is O2, nitrogen is N2, and hydrogen is H2. Those are all your diatomic elements. So if you were to ever get a this sometimes happens with bleach. If bleach is added to a very acidic solution, the active ingredient in bleach is something known as hypochlorite. And if that is added to an acidic or in the wrong environment, that can produce chlorine gas. And if you remember from our first day of class, chlorine gas, Cl2, was used as a chemical warfare agent during World War I. So in the event that you pour bleach onto something and it smells a bit different from how it usually smells, and you're like, man, I think I'm gonna start crying, but I'm not emotional right now. Leave the room. Make sure that you're doing it in an open area, because it's possible that there's a little bit of chlorine gas in there that can cause burns and irritate your eyes, so vacate. So all of these, H. Broncliffe, H2, O2, Br2, N2, Cl2, I2, and F2, those are diatomic elements. So those would all look something similar to what we see in B. Now, when you look at the periodic table, there's some important information on there. Every single element on the periodic table has, and every single periodic table that you look at has at least these three components. It's going to have a whole number, that is the atomic number. If you look at these whole numbers, they are increasing incrementally. So 19, 20, 21, 22, and so on. They're increasing by increment of 1. Then there's the atomic symbol. These atomic symbols correspond to, they are single letters or 2 letters, and they are going to be a sign as to what that element is. For instance, Sr is an element known as strontium. These atomic symbols, they vary a little bit with what their name stems from. There are many of them that are going back to like a Greek translation or a Latin translation of that compound. But then more recently, as I showed just a moment ago, tennessine was because it was discovered in Tennessee. CF, number 98 down here at the bottom, in what's known as the actinide series. CF is Californian because they wanted to misspell how the Red Hot Chili Peppers named their album. Just kidding, just kidding. Just wanted to introduce a little pop culture reference, because the Red Hot Chili Peppers are all going to be timeless. They were popular when I was like 8. Be old. Okay, so your chemical symbol corresponds to either Sometimes it's as simple as the first two letters of the name, or it's just like a reference to the overall name. The last number is, for the most part, in the bottom of that cell, in the bottom of the square. And one of the things that I want you to notice and recognize about those is that it's typically not a whole number. And the reason for that is because you can have different different versions of the same element. Now here I'm going to use a little bit of an example. When it comes to different elements, or when it comes to an element, they're known as isotopes. Has anyone ever heard that term before? If you watch The Simpsons, there's the Springfield Isotopes, that was the baseball team. Or if you like minor league baseball, there's the Albuquerque Isotopes. But an isotope is an element, or isotopes are elements that have different weights. So I always like to think about them as being like green M&Ms. A green M&M is a green M&M is a green M&M. But if I got, 100 different green M&Ms and I put each one of them on a digital balance, the masses of them are going to vary. Would everyone agree with that? They're all green M&Ms, but their masses are a little bit different from one another. We have the same thing with different elements. So there are different isotopes of this compound right here, Fe, or iron, that are going to have slightly different weights. So if I got 5 different atoms of iron, and let's say that, if I went to an enchanted rock, and I found some rock that had iron in it, melted that iron out, and got down to the atomic level, which would be difficult to do. I certainly wouldn't be able to pinch it between my index and thumb fingers. But I've got different isotopes of iron. Chances are those isotopes coming from the same place are probably going to be the same. Does everyone follow me there? If, however, I decided to get, decided to somehow go to the center of the earth and bring back some of the liquid hot magma, and then selected out individual iron atoms there, those are probably going to be different from what I found at Enchanted Rock. They're different isotopes because they're in such extremely different conditions. Does everyone follow me there? Okay. Likewise, if I captured an asteroid and pulled some iron from there, that would probably be another isotope. So isotopes have different masses, but they're the same thing. It's iron regardless of where it's coming from, but it has a different mass. And that's why we have this what's known as an atomic mass, or a weighted average. So then this number, and this gets really abstract, but let's say that I was able to survey all of the iron in the known universe and account for all of the different isotopes. And I'd say, okay, well, here's all the different isotopes. There's 5 different isotopes of iron. One of them accounts for 96% of the different isotopes. So then another one is 2%, another one is 1%, and then the last 2 are about 0.6 and 0.4%. So I have all these different isotopes, but they're not equal in abundance. Is everyone following me there? What I would do is I would take those different abundances and use those to calculate my average atomic mass. So that's why we have this number that goes to 3 or 4 or 2 decimal places. We're taking into consideration all of the different isotopes and their relative abundances. Does that make sense? Now, based on the periodic table and our previous slide, and our previous slide, which of the following is an element? Does anyone think that it's A? What about B? What about C? What about D? Okay, I saw no response to A and B. Would anyone care to say why? That's right, 2 capital letters. That's a great indicator that you're talking about a comma, that you're talking about 2 different elements making one thing. So if you use that logic for A, you can use that same logic for B. C, however, if you look at the periodic table, you see a capital letter followed by a lowercase letter. CO is present on the periodic table, but option A doesn't fit that pattern of capital and lowercase letter. Now, when elements are arranged in order of their atomic numbers, their chemical and physical properties show periodic trends. So when you look at the periodic table, it's always, or if you pull up a periodic table online, you'll typically see them color coded. And before I get to that, we were talking about the diatomic elements. It was H, Br, O, N, Cl, I, and F. So Br, Cl, I, and F, those are all in the same row on the periodic table. They have very similar reactivities. These 4 elements, well, they exist as diatomic elements. The elements that are in the same first row and the second row, those also have similar properties to one another. These elements that are in the middle, in this light blue from 21 to 30, those are also going to be similar in their reactivities from B5 to 9F. Those also have similar reactivity, similar properties. And then this last row over here, from 2 down to 118, those also have similar properties and similar reactivities. These are known as noble gases. They're all going to be very reactive and similar to one another. Now, to illustrate this, we've got a video to show the different reactivities. So here is, this is the sort of thing that I will, okay, so we've got 3 glasses of water, 3 beakers of water, and to each of these different beakers, a mystery gloved hand has added solids to each one of these different beakers. And we will watch mystery. One's on fire, probably not an ice cube being added. The others are bubbling at different rates. One of them just kind of disappeared after it popped. So those were lithium, which in addition to being a fantastic Nirvana song, is element number 3 on the far left-hand side of the periodic table. Lithium, sodium, and potassium. Those are in their pure elemental forms. What they love to do is go through a process known as oxidation. They love to release an electron. When they release that electron, well, they release it and they release a huge amount of energy. Lithium, well, it's not nearly as exciting as something like potassium. Potassium is very exciting. It starts on fire. Here you go. So these elements in their pure form, that's what they're going to do. However, as soon as something like sodium has released all of its electrons, well, then you're going to have something that's not too distant from something like salt water. Now, when it comes to definitions, elements, atoms, molecules, and compounds, a molecule is a group of atoms chemically bonded to one another. So these are your pretty typical colors to represent a molecule. So pictures that you have, or that I will show you in class, nitrogen is typically going to be blue, oxygen is going to be red, carbon is black, hydrogen is going to be white. Here we have a pair of molecules. We have, let's see, hydrogen, oxygen, so H2O. We've got carbon, oxygen, CO2. Then we've got something that looks like this, a little bit more complicated. This has carbon, nitrogen, oxygen, and hydrogen. Now, one of the things that I want you to recognize about this is, let's start in the upper left-hand corner of this structure. We've got a carbon atom, and then from that carbon atom, we have 1, 2, 3 oxygen, or 3 hydrogen atoms. What I want you to notice about this is that this oxygen atom or this hydrogen compared to this hydrogen, they are in different fields. They're kind of they have depth to them, because a molecule like this, like caffeine, which is shown here, exists in 3 dimensions. We have an X plane and a Y plane, so it has a width and a height, but then we're going into the page as well. Does everyone follow that? So these 2 hydrogen atoms, they're not like stacked right on top of one another. Instead, it's almost like these 2 oxygen atoms are these 2 water bubbles. They're far away from one another. One's in my left hand, one's in my right hand, and they are distant from one another. So let's take a minute and write the formula for this structure. Whenever I'm doing something like this, and this is a sort of exam question that you have, I'm going to count up one or a few of my atoms. I always start with carbons. And I start upper left-hand corner and basically go kind of this way. So from the upper left hand to the lower right hand. So I see 1, 2, 3, 4, 5, 6, 7, 8 carbons. So I'm going to write this, and the convention is that I'm going to write a capital C and then with a subscript of 8. Just like we did with H2O. Next, I'm going to go after my nitrogens. 1, 2, 3, 4. So N 4. Now my oxygens. 1, 2, done. Last but not least, my hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogens. Does everyone agree with that breakdown? Okay, any dissent? Or does everyone follow how I did that? Okay. Did I count them all up right, or did I miss something? Why did I write 2 hydrogens? How many hydrogens do we have? Good job, good job. Got y'all to stay on your feet there. I don't know why I wrote 2. Okay, scribble, scribble, scribble. I could press erase, but we've come this far. Thank you very much. Okay, now, is everyone good with that? Okay. This is how you write a formula. There are some conventions in like the sequence that you write elements to put together a formula. Typically carbon and hydrogen are next to one another because typically there's lots of carbons that are bound to hydrogens, which if we look at all of our carbons, almost all of them are bound to at least one hydrogen. Not every single one of them, but most of them are. Okay, so then if we were to look at ibuprofen, It has a chemical composition C13H18O2. How many hydrogens are in ibuprofen? 18. Are you going to have a test question of this level? You might have one. I like to throw some low-hanging fruit out there, but then next is going to be a little bit more challenging. How many hydrogens are there in the expression 3? So we have a coefficient out in front, implying that there are 3 of this particular molecule. 18 times 3 is 54. You're absolutely right. How's everyone handling all this so far? You guys want to just take the test right now? Good, because I haven't written it yet. Even though I think some of you are probably like, yeah, I guess. Okay, that's where we're going to stop today. So I will stop the recording